All right, yeah. Today we're moving on to talking about the depth-first search algorithm. So that plays a central role in several graph theory algorithms. So let's start by talking about what is a DFS, a depth-first search algorithm. So it is a core algorithm in graph theory. So it allows to explore nodes and each edges of the graph it allows to traverse through the graph. So that is a form of traversal algorithms. So an interesting thing about this, a nice thing, to put in other words, that it is really easy to code, and it runs in a time complexity of big O of V plus E. That is vertices plus edges. So it is directly proportional to the size of the graph. So by the way, it is pretty efficient on the time complexity. So by itself, this depth-first search algorithm isn't that useful, but when it is augmented with another to perform other tasks, it becomes very efficient on such tasks as checking if the graph is connected. So that is determining connectivity, counting connected components, finding bridges, minimum spanning trees, articulation points. So in these applications, DFS really shines. So let's look at the example of depth-first search, how it traverses through the graph. So as its name suggests, it plunges in depth first into a graph. Without regard for which it selects next. So it just plunges depth first. So until it cannot go any further, at which point it backtracks and continues to an unvisited node. Alright, so let's start our depth first search with 0 node. We're now picking an edge outward from 0. We can go to 9 and 1. Let's go to 9. So in this case, we can go to node from node 9 only to node 8. So there is only one edge from node 9, that is 8. And here we can go to 1 and 7. We're randomly picked to go to node 7. And alright, if we go to node 10 and then 11, notice that we cannot go to node 7 once more, so we are making sure we do not revisit visited nodes. So if we have visited node 7 before, we cannot visit it. So we cannot create a cycle here using depth-first search algorithm. So also in this case, we can determine if a directed graph has cycles, and on undirected graph using this property of depth-first search, we can check if a graph is a tree, and also how to say that, we can make a tree from a graph. So in this case, there are a lot of applications of depth-first search. All right, let's look at how it traverses. So since we cannot go any more further from node 11, we'll backtrack first to 10, then to 7, and from node 7 we can go to, there are some more neighbors within node 7, that is 3 and 6, so we can go to node 3, for example, and from there we'll go to node 2. And so from node 2, we cannot go any further, so there is no edge from node 2 to somewhere. So that is a dead end, and we're backtracking if it is reached. So as in this case, we're backtracking to 3. 4 is another dead end, so another time we're backtracking to 3, and now we're going to 5, 6. We cannot go to 7 once more. So we're backtracking 6, 5, 3, 7, and 8. So now we are back to 8. There is another neighbor of 8 that has not been visited previously. That is 1. So we're going to 1 and back to 0. So in this case, we can, now we're backtracking back to 0, and that is how depth first search works in a nutshell. Yeah, so that is the algorithm, how it this is the how it works. So also notice that we haven't visited node 12 because it is not in this component, connectivity component, and we cannot visit it from while traversing this graph, of course. So in this case, we can also check if the graph is connected, and also can't connect the components, but we'll talk about it a bit later. So let's look at some pseudocode for depth first search. To get a deeper understanding how it works. So the first thing we need to declare is global variables. So that is n, the number of nodes in the graph. G, that is the adjacency list that represents the graph, and also visited array, vector in C++, for example. So a visited array. So that is a Boolean array that contains only false values, and it is size of n. So it determines if whether or not node I has been visited for any index I that is in the list. That for any index I less than n. So also at the beginning, that is of course false. We haven't visited any of the nodes yet. And also instead of using visited nodes, visited array, sometimes it is used color array, but we're going to also talk about it a bit further. So at the main function, this start node, we're declaring the starting node. So once that setup of the variables, we're defining our starting node. So that is 0 because we're starting our depth first search from 0. We can start it from any other node, but this time, for example, and also sometimes, usually it is written DFS of 0, not of start node, but in this case the code is just a bit more readable, because why are we starting from 0? Because that is the number of node, and not as in the recursion function, it means something else. So we're calling the DFS method, and let's look at what is inside it. So a DFS, this function, has only one argument, that is at. So that is just at which node we're currently at. So now the block of some logics that is that if the node we're currently at has been visited previously, that means we're returning. So that means that there is a cycle in this. If this is directed graph, there is a cycle in a graph. So we're just returning. We do not want to handle with this because in the depth first search, the algorithm is that we cannot look through the node twice. Of course, we cannot traverse it twice. So now to explore all the neighbors of the node, because we are doing this recursively, and also the depth first search traverses in depth. So because it is in depth, we must have a recursion function, because it is very I think it is very complex to write it without recursion. So as we're using recursion here, we need a base case to leave the recursion. So that is this logic block with if we're visited this node before, we're returning. All right, and next we are making this node, the value of this node in visited array equal to true because we've visited this node, and we're going to each of its neighbors recursively, looping over them and calling recursively the DFS method. So because we're calling it recursively, it goes in depth. All right. So by the way, that is what the DFS in a nutshell in its code implementation for pseudocode. And by the way, it is very basic in comparison to other types of traversals. So that is just we're looping through every node. That is the main part of the algorithm. That is just three strings of code, and this is just the checking if it is, if we've visited this node before, the declaring of variables and the main part. So it is one of the most simplest algorithms on graph theory. And so and let's look at the one of the implementations, one of the use cases of where we can use depth first search. So that is the counting connected components, and we can also check connectivity with the same algorithm. All right. So first let's understand what we mean by counting connected components. So a graph might be split into multiple disjoint components, and if we want to count them, it is because it is useful to be able to identify them and count these components. One way to identify these might be to color them, to tell them apart. But what does coloring nodes really mean to a computer? So that means that each color has its own ID. We're assigning an integer value to each group. We can call it color. The array of these colors is most often called color. However, we can call it ID and whatever. So here, for example, purple has the ID of 1 and green has the ID of 3, whatever. It is not that important. So we can use depth first search to identify components. So first, we're looping through every node in our graph. So if we have not visited it from 0 to n, first we're making sure all nodes are labeled from 0 to n, and then the algorithm is that we're starting, we're looping through every node in our graph. So if it has not been already visited, that means we want to start DFS on this node and mark all reachable nodes with the same component ID. Let's look at the algorithm. So we're starting with 0, and 0 has not been visited already. So we're starting DFS from this node, from 0. We're making DFS with the algorithm we've looked, traversing now to 8 and going to 4. In this case, we're traversing through every node of this component and assigning its ID to 0. Now the next now for node 1, of course, node 1. So we have not been visited before, and we have not assigned any color to this node. So we're starting depth first search as well on this component. So we're assigning its value of this component to 1, assigning the value of the array of each node to 1. yeah, so backtracking it back, and so on for other components. So by the way, this is pretty obvious algorithm. So we're just traversing through each node of each component and assigning the color, yeah, the ID, and counting its value. All right, so here let's look at some pseudocode for how this works. So first we're declaring a couple of things, that is, and the number of nodes, and then the graph G at the adjacency list, representing the graph, the same thing as for the basic depth first search. Now, count and components, and this components array is also called color array, so that keeps track of each ID of each component. So next we're checking if the graph is visited or not, or if the node is visited or not. By the way, here the visited array might be useful, but it is not it is not necessary here. So it is not necessary here, because we can use components array to identify has this node a component. So first we can assign each component ID to be equal to -1, -10 in the power of 9, something like that, or -infinity in different languages. We can call it in other ways. So assign it to value that cannot have we can assign value that cannot be an ID of some node, of a node, and check in this way. All right. So next, let's look at the find components function method. So we're looping through every node, and if the current node has been visited, has not been visited, then we're executing some logics. This logics is just we're incrementing the count. The count, we can call it the current color also. That is just the current color. And the next we're starting depth first search. And this depth first search differs slightly from the previous, so that is just the modified basic depth first search. So here we're checking first. So one moment. We've looked at what is inside the DFS. So we're looking at DFS. So inside it, the function, we mark that we have visited this node, and so as in the basic DFS, and next we're assigning the components or color array value to be equal to count, that is our current node, and also the next step we're doing is that we're starting to traverse. We're iterating. We simply iterate over every neighboring node that has not been visited yet. So if it has not been visited, we're starting depth first search. We're continuing depth first search method to explore them as well and assign their value as well. So we're back inside the DFS method, the find component method. After that, we're simply returning this method simply returns the count, the amount of connected components, and the components array that contains the information about which components each node belongs to. All right, and another thing I wanted to talk today is what else can DFS do. So we've covered two things it can do. just traverse a graph and also find connected components. Yeah, and counting these connected components. So it can compute a graph's minimum spanning tree. That is a tree that consists each node of the graph, and it has the minimum cost, so that is only on weight graphs. And also it can detect and find cycles in a graph, check if the graph is bipartite. So can we split a graph into two groups, and within each group the nodes are not connected. Within which group? Within each of these groups, nodes are not connected with each other. And also we can find strongly connected components, that is also on directed graphs. We can topologically sort the nodes, so the differences from basic depth first search code and topological sort of a graph, or of the nodes of the graph, is the difference is in two strings of code. Also we can find bridges, articulation points, and argumenting path and flow network. So these are the applications of this depth first search algorithm. So we can see that it is a very useful algorithm on graph theory. So I'll wrap up here. Thank you. That is what about the depth first search. Next time I think I'll talk about breadth first search. So
okay, great, good talk. Yes.